Exploring information content on mobile devices can be tedious and time-consuming. For instance, a user planning to purchase a camera might get frustrated or tired by constantly having to switch between the list view and the detailed view. Similarly, a user browsing for hotels listed on a map finds himself checking the details of each item one by one. The task is further complicated by frequent panning or zooming and selecting small or overlapping items. We present Around Device Binning, or AD binning, a novel mobile user interface that allows users to offload mobile content into the space around the device and retrieve it when required. To determine AD binning's input range, participants were asked to draw a half circle around the device with their right hand. Results show that users can comfortably reach up to 40 centimeters from the device. We split this circular space into 5 sectors to spatially enhance item recall. We conducted 3 experiments to explore AD binning's design space in detail. We started with the selection methods and finding the smallest feasible target size. We tested 6 selection methods. Tap, select by tapping on the screen. BackTap, tap on the back of the device. Dwell, keep the finger static for some time. LiftOff, a sudden upward lift from the current finger position. Pierce, by piercing down through an imaginary plane defined by the device. DownUp, a downward motion followed by an upward motion. Though tap and dwell have the least errors and faster selection times, this does not guarantee their practicality in all applications. Therefore, we chose to continue with BackTap and LiftOff. We further investigate different space discretization techniques and binning locations. With the uniform discretization, the available space was divided into equally sized bins. In the distance-dependent discretization, the sizes of the bins were gradually increased from the inner cells to the outer cells. Fisheye was designed to provide more space to the currently selected item. We observe that the fisheye discretization equalized error rates and trial times across target distances. We then compared binning techniques that provide varying degrees of user control in item placement and retrieval. The tap and bin technique allows a user to pick up items and move them to the desired AD bin to drop it using a lift-off gesture. With flick and bin, a user bins the item to the desired AD sector by flicking it in the corresponding direction. And with automatic binning, the system automatically assigns each item to an empty bin. For all techniques, item retrieval ends with a liftoff in the currently selected bin. Results show that participants were faster with tap and bin due to the memory-enhancing effect of spatial encoding. We move ahead by demonstrating and evaluating a practical AD binning usage scenario for browsing information content. We asked participants to find the cheapest hotel with a specific rating ranging from 1 star to 5 stars from a map using typical on-screen methods and AD binning. Results showed that participants were significantly faster with AD binning compared to the on-screen technique. We now demonstrate applications for which we can apply our results for off-screen interactions. In this sample application, camera search results are offloaded around the device. Users can browse through them by moving their hand around the device. This reduces the amount of switching between the list and detailed views. Searching for mail in an inbox can be time-consuming, but we can organize and place emails into the space around the device. In this example, AD binning sectors are divided into days, where each day is subdivided into different times. Users can directly access their mail by navigating to the desired AD bin. The AD binning technique can also be used when the device is on a surface. The user interacts with different items by touching the surface area. Overall, we demonstrated that AD binning is a promising enhancement to mobile interfaces involving large amounts of data.